My name is Heike Hoedt of the Germany-based engineering office Simply Solar. I want to present the Gari project to you. It's a LEAP-3 project for the development of a modern solar cooking solution for African staple food in the framework of the long-term European-African Partnership on Renewable Energies program of the EU. We developed as the technical partner in the Gari project. As an example, the processing of cassava into Gari with solar energy. Here you see the current traditional way of processing Gari. Cassava is grated, dehumidified, fermented, and then roasted over large pans over open fire, usually by women, accompanied by children. Cassava is a plant that is quite large. You see it in the left picture. It develops roots which are starchy, very starchy. You see them in the right. And they have a very low shelf life of only a few days, like 2 or 3 days, before they decay. So people prefer to process them into a kind of a very coarse flour, which is called Gari, and it's used over a number of countries where cassava is grown. You could say it's a commodity food. The advantage is that cassava then has a long shelf life because it's dry. It can be easily stored, it can be easily transported. In the LEAP-3 project Gari, we first of all analyzed the process itself. You see on the left side over improved cook stoves with wood fire. Women are roasting Gari. This is already an improvement to the energetic side and also to the air pollution side of the process. On the right side you will see a photo of our result. Here you see the whole value chain of the Gari production. After harvest, the cassava is peeled and washed. It is then grated, usually with electric graters or large fossil fuel driven graters. Then it is dewatered through pressing it and fermented as per the local preferences. Some places they like to ferment it up to 3 days, so the taste is more sour. In other places it's just a mere few hours of fermentation. After that, the roasting takes place. Technically, we might not say that it's a roasting because the process happens only at a maximum of 120 degrees. It happens in large open pans, and the main energy required here comes in form of heat. After that, the product is weighed and packaged. The process we looked at, the part of the process we looked at in Gari was particularly the roasting process. And we developed 3 solar thermal options for producing Gari with solar energy and tested them at the University of Lomé, where the agricultural department was a project partner in the Gari project. The 3 technological options which we developed was a roasting Gari directly with photovoltaic energy, that means without any battery. Then secondly, processing Gari with low pressure steam that is generated by photovoltaic electricity. And third, processing Gari with low pressure steam generated by Scheffler reflectors. I want to show you those 3 options in a little bit more detail. Here you see the direct solution. On the right side, the scheme showing photovoltaic panels hooked to a controller that matches the PV power and the heating power, and a pan with direct heating through electric resistors. On the left you see that we mimic the local pans, which are kind of open Gari type pans. Yeah, this obviously means that there is no storage of energy, and as you process the Gari, you depend on the power input that comes directly at that moment from the sun. So any clouds or less power in morning and evening, these things are directly reflected to the behavior, to the heating behavior of the processing vessel. The second solution which we developed was using low pressure steam, which is generated by photovoltaic electricity, and we use what we call a PV steam cube. If we go through the scheme here, you see the photovoltaic panels in one feed electricity to the PV steam cube 2, which is a storage unit. It's a thermally insulated metal block. We use metal as storage media, which is heated up to 400 degrees by means of electric resistors. There's a control unit that handles the temperature distribution in the storage block and manages the PV power input. You see in yellow the resistors, and in blue and red you see the pipe register, which is our heat exchanger to extract energy from this storage. We can use the PV steam cube, the storage block, between 150 and 400 degrees to extract steam at any time. 3 and 4 are the pump and the water supply. The water is used as a closed loop, which means that as soon as somebody switches the pump on and regulates it to the desired power, water is injected into the steam cube and steam is generated at the instant and goes through what is a red line here, through a pipe, into the double-walled processing vessel. Here the vessel is shown very cylindric, but for Gari roasting it's usually more shallow, as you saw in the photos. And we did that in the real adaptation of this technology. So the steam at a rather low pressure can still provide 110, 120 degrees, and then it condenses in the vessel, in the double wall of the vessel, and is recirculated back into the feed water tank. Number 4 is the feed water tank. We have the option here to hook the electric grid to the PV steam cube. Number 6 is resembling the electric grid. That makes the option more versatile. You could even, if you've processed a solar energy, let's say through the whole day, you could continue and charge it with grid electricity if you wanted to, and continue processing. The PV steam cube is very well insulated. Even if you're not using it, you can preserve the heat for several days. This is what it looks like in our demo setup at the University of Lomé. On the right you see the PV steam cube, and on the left you see the processing vessel. The third alternative option which we developed here was using solar concentrators. Those are 2.5 square meter Scheffler reflectors for steam production, which then is used in the similar setup like the PV steam cube, a double-walled processing vessel that is heated by steam. In the picture you see that in Lomé we installed 6 reflectors set up as pairs. Each reflector has his own receiver for the concentrated light, where an aluminium receiver, which also acts as an interim storage of energy, is heated directly by the focal point, and then in a very similar setup as for the PV steam cube solution, the user can switch on a pump. The feed water is inserted into those receivers and steam is generated at the instance. The storage capacity of this system is not very high. These receivers have around 10 kg weight each and therefore are interim storage. So this system can buffer, for example, a few clouds that cover the sun for a while, but not more than an hour of heat is stored here. Whereas the second solution with the PV steam cube, in this case, in the demo unit, we had a 70 kg storage unit and can store much more energy. The results of the Gari project were that we had a successful proof of concept. All three solutions are able to produce Gari to the known quality of this product, which was analyzed by one of the project partners in the Stellenbosch University in South Africa and also in University of Kassel in Germany in the agricultural technology faculty. And so the product result was very good. As expected, in the very tropical climate of our demo unit in Lome, the PV solutions perform better than the reflector technology, because when the climate is very humid, reflector technology is not getting enough direct light to be viable. But this project aimed at a transferable product, which means a transferable technology, which means that what we develop should be fit to be transferred to other countries. And obviously, if you think about countries in the Sahel or so, you have a lot more direct sunlight, then reflector technology becomes very interesting. We also saw that the direct use of photovoltaics is not so comfortable, but of course the cheapest solution, because solar panels are cheap and all you need is a processing vessel and a controller, no other components. But because the power output is directly linked to solar gain, it's not so comfortable. The project also aimed at the transferability to other products. So we're thinking about using it for corn flour, for NSAID or banana starch, but this has not been tested in the project from the food processing side. Thank you for your attention. You're welcome to ask any questions.